All right, hello everyone. This is Dr. Gallenstein, and today we are doing lecture number 6. All right. In lecture number 6, we are going to continue our series discussing ordinary least squares, some of the math that goes into how do we calculate the various components of a regression model. And then, again, we're going to continue our discussion of some of the various problems or challenges that can arise when the assumptions of the ordinary least squares model do not hold. And specifically today, we're going to talk about something called multicollinearity. You remember from last time we did omitted variable bias, and today we're going to do the problem of multicollinearity. That's going to be the main theme. We're going to start out looking at how do we calculate goodness of fit measures. Okay, we're going to look at that first, and then we're going to do multicollinearity for the rest of the lecture. And as is typical, I will demo it at the end in Stata. All right, so with that, let's get started. So first thing, goodness of fit. I want to do this in this lecture. One is I just kind of want to show you how to calculate the goodness of fit measures. Specifically, we're going to do R squared and adjusted R squared. I'm going to show you how to calculate those. And then we're going to use some of that notation later in the lecture. So it kind of makes sense that it's here, even though I called the lecture multicollinearity. This kind of is connected. All right. So let's do it. Goodness of fit. How do we calculate it? All right. Now let's think back. Let's think again about how good a model we have. You remember from lecture 3, we introduced the concept of R squared. R squared is a number between 0 and 1, and the higher that R squared is, the better our model is, right? Or I should say, how well it fits the data. All right. Now, here in the next couple of slides, we're going to show you how do you calculate R squared. Where does it come from? What does it mean? All right. Now, remember, so we're going to use this word fits. We say that a model fits the data if our model can explain the variation in the dependent variable. All right. So our model fits the data if it can explain the variation in the dependent variable. So we can express the total amount. All right, so this is what we're going to do. We're going to take the total amount of variation and we're going to break it into parts. All right, that's what we're about to do. Okay, so we can express the variation in the dependent variable as something that we call the total sum of squares. The total sum of squares, which we abbreviate SST, so we put the T at the end, I'm not sure why. We also can say sum of squares total, I think that's where that is. Okay, and so this expression here communicates us. It's a measure of the total amount of variation in the dependent variable. All right, this SST is the total amount of variation in the dependent variable. Basically what it is it's the difference between each particular observation and the mean squared and then summed up over all the possible observations. All right, this is the total sum of squares. It's the total sum of squares. All right, this is a measurement of the total amount of variation in the dependent variable. All right. Now, we can express the amount of variation that is explained in the model, or explained by the model, we could say, as what's called the explained sum of squares. All right, the explained sum of squares. And the explained sum of squares is this expression. Okay, this is the amount of variation in the dependent variable that is explained by the model. All right, so what does it look like? It is the predicted dependent variable, so the predicted value of y, predicted from your model, from the estimated model. Okay, the predicted y for each individual minus the mean squared and then summed up over all individuals. All right, we call this SSE, the explained sum of squares, the sum of squares explained. All right, so this is a measurement of how much of that variation is explained by the model. All right, and then lastly, we can express the unexplained variation in the dependent variable as the sum of squared residuals, or the residual sum of squared. All right, the sum of squared residuals. All right, so in this case, we're looking at the residual. You remember this from last lecture. We're looking at the residual, the difference between each individual observed dependent variable value and the predicted dependent variable squared and then summed up. All right, so SSR is a measurement of how much of the variation in the dependent variable is not explained by the model. SSE is a measurement of how much of the variation in the dependent variable is explained by the model. So then the total, so they sum to the total, so SST equals SSE plus SSR. All right, so the total amount of variation of the dependent variable is equal to the amount of variation that is explained by the model plus the amount of variation that is not explained by the model, or the amount of variation that's captured by the residuals. All right, so this is the total sum of squares, the total amount of variation in the model, in the dependent variable. All right, now using these measures, we can come up with a measurement of the goodness of fit. Now let's think about it intuitively just real quick first. So if I want to say, how well does my model fit the data? Well, then what I would say is, okay, well, how much of the variation in the dependent variable is explained by the model? Well, one way to get that, one way to get like a percentage of that would be to take the sum of squared explained, that means the total amount of variation that is explained, and divide it by the total amount of variation. All right, and that's what we call R squared. So our goodness of fit measurement is the percent of the total variation of the dependent variable that is explained by the model. All right, so that's our R squared. Now, there's one major problem with R squared. And we talked about this last time, or in the past. It increases every time that you add a new variable to the model, even if the new model is if the new variable is irrelevant. So for a multivariate regression model, R squared is not the best measure of goodness of fit, right? So what we need, or what we want, is we want to use what's called the adjusted R squared, or this. We're going to use both of them combined, but we can also use the adjusted R squared. All right. And the adjusted R squared is calculated this way. The adjusted R squared is a function of the R squared. All right, it's 1 minus, and this big clunky term here, 1 minus R squared times n minus 1 over n minus k minus 1, where n is the sample size, and k is the number of independent variables, excluding the constant, so it doesn't include the constant. So n is the sample size, and k is the number of independent variables. Now, why is this better? Why does this help? So what happens is that the adjusted R squared penalizes you for including additional variables. So it only is going to go up if you add relevant variables. Well, what do I mean by that? What do I mean by penalize you? What I mean is that as you increase the number of independent variables, the adjusted R squared will go down. Unless, of course, those variables improve the fit of your model. Why is that? Well, we can look at the equation. We can understand why. K is the number of independent variables. K, here, you can see, as K goes up, the denominator of this fraction, the denominator goes down. As K goes up, the denominator goes down. As the denominator goes down, this total term, this fraction term, gets larger. As the fraction term gets larger, 1 minus the fraction term gets smaller. All right, so there's several steps here to see it. But if you think about this algebraically, as k gets bigger, the adjusted R squared will get smaller. All right, and so if you add a variable that's not relevant, if you add a variable that is not relevant, then the adjusted R squared is going to go down. The only way that it will go up is if the R squared is going up, if it improves the fit enough to compensate for the reduction that's caused by the inclusion of an additional variable. Okay, so there's your adjusted R squared. All right, that's how you calculate it. Be ready to calculate it. All right. So that was just kind of a quick thing there. Some of that notation we'll use later. But so at this point now, we're going to transition into the main kind of thrust of this lecture. We're going to talk about multicollinearity, okay? But we're going to take some steps to get there. All right, we're going to set up a few things first before we get there, and then we'll talk about it in detail. Okay, so what we're going to do to set this up is we're going to first talk about the variance of beta hat 1, beta 1 hat. Okay, we're going to talk about the variance of our coefficient estimate. All right, this is going to be a very important topic. All right, and it's going to relate closely with the issue of multicollinearity. All right, now first, remember that our coefficient estimates, each one of our coefficient estimates, in this case we're just kind of using an example of beta 1, that's kind of our go-to coefficient, okay? That our coefficient estimate is a random variable. For every sample of data taken from the population for which you run the regression model, there will be a new value of beta 1 hat. There'll be a new estimate. All right. So therefore, beta 1 hat will have some distribution. There will be a distribution of possible beta 1 hats. All right. This is kind of like, if you remember, the sampling distribution of the sample mean. It's kind of a very similar concept here. All right. Now, if beta 1 hat is unbiased, that means that this distribution will have a mean that is equal to the true population beta 1. All right, so let's visualize this. So there's going to be some distribution of beta 1 hat. All right, again, think back to the sampling distribution of the sample mean. All right, every time that you have a sample of data and you run the same regression model, you will get a different value of beta 1 hat, okay? And that beta 1 hat will come from some distribution of possible beta 1 hats. All right. We're saying right here beta 1, the true beta 1 equals 10 in this illustration here. And so if beta 1 hat is unbiased, then it will be centered at the true population mean. We talked about that in the last lecture. All right. And it will have roughly a normal distribution. So that means it is most likely to find beta 1 hat values near the mean, and it's very unlikely to find beta 1 hat values that are way off in the tails. That means much bigger than the mean or much smaller than the mean. All right. Now, because this has a distribution, we can say that there is a variance of beta 1 hat. All right, so the variance of beta 1 hat is a measure of the dispersion of the possible beta 1 hat values. How wide is this distribution? Variance gives you how widely distributed the data is. All right, so that's the distribution of beta 1 hat. All right, so we can use the variance of beta 1 hat. All right, now let me drive this point home. I want to make this point really clear. What we're talking about when we're talking about the distribution of beta 1 hat. All right, that way we can understand the variance. All right, so we're going to go back. I'm actually going to use a very similar example that we used when we were talking about the sample mean and the sampling distribution of the sample mean. So you're going to remember my orange farmers, my population of orange farmers. I believe this is from the second lecture number 2. So you'll remember my orange farmers. This is my total population of orange farmers. And there is a true beta 1. All right, let's say we're doing some research. We want to know the effect of hybrid seeds, so kind of advanced seeds, on yields. All right, so what's the impact on farmers' yields if they use advanced seeds? Well, that impact is beta 1. All right, now if we look at the whole population of orange farmers, beta 1 is the true population relationship between yields and the use of hybrid seeds. All right, we're saying that it's 10. But we don't have information on the whole population. So instead we collect a sample of data. We collect data from these blue farmers, and we'll estimate our model, and we will find an estimate of beta 1 hat. All right, so Beta 1 hat is the estimated relationship between yields and the use of hybrid seeds that we find with the blue sample. And let's say that the blue sample gives us an estimated beta 1 of 9. All right. So we run we have the same regression model, but we run it on data from just the blue farmers, and we get beta 1 hat equals 9. Well, then we go back, we collect another sample, this time the green farmers, and we run the same regression model, and this time we get a green beta 1 hat. We get a different beta 1 hat estimate, and this time it's going to be equal to 13. All right, and then we go back, and this time we collect data from the red farmers. We run the same regression model, and we get an estimate of the beta 1, so beta 1 hat, the red beta 1 hat, and it's going to be equal to 10.2. All right, so basically what I've said here, what I've shown, is that as we collect different samples from the population and run the same model, we'll get different estimates for beta 1 hat. All right, so those different estimates will be found on the distribution. So it's much more likely to get a beta 1 hat estimate that's near the mean, and much less likely to get a beta 1 hat estimate that's farther away from the mean. All right. And how widely distributed this distribution is will determine kind of how likely it is to find values that are far away from the mean versus close to the mean. All right. So let's keep driving this point home. So the larger the variance, the wider the distribution of beta 1 hat is. All right, so here in this graph, I'm showing you 3 different distributions of beta 1 hat. I have a black distribution, a purple distribution, and a red distribution. The black distribution is the smallest variance. That means it's most likely to find values of beta 1 hat near the mean for the black distribution. It's less likely for the purple and less likely for the red. The red has the widest distribution. The widest distribution of beta 1 hat. That means it's less likely to find a value of beta 1 hat near the mean and more likely to find a value of beta 1 hat above the mean or below the mean. Okay, so the larger the variance, the further away from the mean we might expect to find any particular value of beta 1 hat in our particular sample. All right, so we are more likely to see an estimate around 14 for the red distribution than we are for the purple distribution than we are for the black distribution, for example here. All right, so we would prefer to have a variance of beta 1 hat that's smaller. The smaller the variance of beta 1 hat, the more precise the estimate is. So that is to say that the smaller the variance, the more likely it is that we will find a beta 1 hat that's close to the true beta 1. So we would prefer to have this black distribution than to this red distribution. Because, and let's think about this, we typically only have one. We typically only have one set of sample data. We only have one data set. And so we only get one beta 1 hat estimate. We usually don't have several different samples from the same population. So we only usually have one beta 1 hat. So we only have one estimate of beta 1 hat. Okay, and so it's very important to us that that beta 1 hat estimate is close to the mean. It's very important to us that it's close to the mean because we only get one shot. And so we don't want our beta 1 hat distribution to be like the red one because it's much more likely that that one beta 1 hat that we get is really far away from the mean. All right? It's very important because if beta 1 hat is unbiased, then beta 1 hat, the mean of beta 1 hat is the true population beta 1. And that's what we want to know. We want to know the true population beta 1. And so we want our distribution to have a small variance. That way it's much more likely to find a beta 1 hat value that's close to the mean, that's close to the true beta 1. We don't want a huge distribution because it makes it more likely to find a beta 1 hat that's further away from the mean. So we call this, we say that our estimates, if let's say we have the black distribution, our estimates would be more precise. That means they're more likely to fall close to the true population beta 1 than if we had the red distribution. If we had the red distribution, they're less precise because it's much more likely to find a value that's farther away from the mean. So larger variances of beta 1 make hypothesis testing harder. So that is, it makes it more difficult to detect a statistically significant coefficient. If we have a really wide distribution, then it's much more likely to find beta 1 hat values that are large or very small, which makes it harder to reject the null hypothesis. We would need an even larger value of beta 1 hat for us to be able to reject the null hypothesis. So we do not like large variances. When we have large variances, that makes it much more difficult for us. That makes it much more difficult for us to reject the null hypothesis that beta 1 hat is actually equal to 0. All right. And then lastly, beta 1 hat estimates that have very wide distributions, we call this inefficient. They are inefficient. They're inefficient because it's difficult to reject the null. It is likely to find extreme values far from the mean. All right, so beta 1 hats that have wide distributions, if there's a wide distribution of beta 1 hat, that would make it, we call it inefficient. All right, inefficient, and that's going to be the problem. So inefficient or imprecise. That's going to be the problem that's going to be caused by multicollinearity. We'll get to that in a minute. Okay, so larger variances of beta 1 hat make hypothesis testing harder. That is, it makes it more difficult. To detect a statistically significant difference. So therefore, the variance of the estimate is very important to us. We do not want our estimated beta 1 hat to have a very large variance, because then we will have a difficult time finding statistically significant results, even if there really is a correlation in the population. Put another way, if the variance of beta 1 hat is very large, we will have a high chance of committing a type 2 error. All right. So let's drive this home by talking about how we calculate the variance. How do we calculate, or as you'll see in a moment, estimate the variance of beta 1 hat? All right, let's talk about that. So to do that, we are going to consider a generic multivariate regression model. So here's just a generic multivariate regression model. We have a dependent variable y, and it's regressed on 3 independent variables, x1, x2, and x3. We estimate this model and find beta 1 hat, beta 2 hat, and beta 3 hat. We want to know the variance of beta 1 hat, okay? So in this example, we're going to be interested in how do we calculate the variance of beta 1 hat. So how do we calculate it? All right. So let's first consider the generic case, just the generic equation here. The variance of beta j hat, so j is just an indicator for different independent variables. So j could be 1, and that would be beta 1 hat. J could be 2, that would be beta 2 hat. J could be 3, which would be beta 3 hat. All right. So the variance of beta j hat. All right, so the variance of beta j hat is equal to this expression here. And again, I'm just going to be clear. J indexes the independent variable. So we have a k number of independent variables. So j could take any value between 1 and k, any integer value between 1 and k. All right. So here's our equation for the variance of beta j hat. Let's fill in the blanks. Sigma squared is the variance of the error term. All right, so the variance of the error term is sigma squared. All right. So variance of beta j hat is a function of sigma squared. SSTJ. SSTJ, this is the total variation of the independent variable xj in the sample. So this is where we're kind of using the same notation that I used above when I was talking about the goodness of fit measure, this SST. Except in this case, I'm not talking about the total sum of squares of the dependent variable. In this case, I'm talking about the total sum of squares of the independent variable xj. So SSTJ equals the total sum of squares of the independent variable xj. All right. So this is a measurement of the total amount of variation in the independent variable xj. All right. And then lastly, the last term here, r squared j, r squared j is the r squared value taken from a regression of xj on all the other independent variables. So let's say we're thinking about x1, so the first independent variable. It would be the r squared that is taken from this regression. The regression of x1 regressed on x2 and x3. This is where you would treat x1 as the dependent variable and x2 and x3 as the independent variables. And I'm using alpha to note the coefficients in this regression. So this is the coefficient on the intercept term. This is the slope coefficient on x2. This is the slope coefficient on x3 plus some error term. All right, so sigma squared is the variance of the error term. SSTJ is the total amount of variation in the independent variable. And then r squared j is the r squared taken from a regression of the independent variable xj on all the other independent variables. So in a sense, we can say that r squared j is capturing the amount of correlation between the independent variable xj and all the other independent variables. All right, so now we're just going to look at the specific case of we want the variance of beta 1. And so we've got the variance of beta 1 equals sigma squared, the variance of the error term, divided by the total amount of variance in the independent variable x1 times 1 minus r squared 1, which is the amount of correlation between x1 and the other independent variables, so x2 and x3. So from this, we can see that the variance of beta 1 hat depends on the amount of variation in the error term and the variation in the independent variable. So that's what we have here. The amount of variation in the error term and the variation in the independent variable. It's also a function of the amount of variation between the independent variables, but I'll come back to that later. Okay, so if the error variance increases, that means if the amount of variation in the error term increases, then the variance of beta 1 hat increases. All right, we just look at the fraction, we can see that. As sigma squared goes up, the variance of beta 1 hat goes up. If there's more variation in the independent variable, the variance of beta 1 hat decreases. All right, so that is SST. So as SST goes up, so if there's more variation, in the independent variable, then SST will go up. And as SST goes up, the variance goes down. All right. So we want smaller variances of beta 1 hat. All right. Therefore, we want to reduce the amount of variation in the error term, and we want to increase the amount of variation in the independent variable x1. This will give us more precise estimates. Right? We always want a smaller variance of beta 1 hat. Now there's one direct way to reduce the variance of beta 1 hat. The easiest way, although we rarely are able to do it, but the most direct way to do this is to increase the sample size. Collect more data. Collect a larger sample from your population. Because as the sample size increases, the variance of the error term does not change. So sigma squared does not increase as the sample size increases. However, the amount of variation in your independent variable x does increase as the sample size increases. So if you increase the sample size, SST will get larger, which will, and nothing will happen to sigma squared. And so your overall variance will go down. So the most direct way to reduce your variance is going to be to increase your sample size. All right. Now, so this is the expression for the variance of beta 1 hat. Now, when we look at this, we actually have a problem. And the problem is that sigma squared is the variance of the error term. It's the error term from the population regression function error term. Well, what do we know about the population function? We know that we don't have it. We don't have all the data from the population. So we don't know the population error term. All right, so we actually can't calculate this because we never know what sigma squared is. We can't calculate it because we don't know what sigma squared is. So instead what we do is we have to estimate it. We have to estimate sigma squared. All right, so we do not observe sigma squared because sigma squared is the population error variance, and we do not observe the population error. Therefore, we have to estimate the variance of beta 1 hat, and we do this by estimating the population error sigma squared. Our estimate is sigma squared hat. We use the residuals from the regression as a basis for our estimate of the error variance. All right, so we use the residuals from the regression as a basis for our estimate of the error variance. All right, so now let ui hat equal the residual from the regression. All right, I'm going to use ui hat as we continue here. In the past, I use ri. But I think UI is going to be a better notation. All right. So UI hat is the residual from the regression model. All right. So what we're going to do is we're going to estimate the population error term. The population. We're going to estimate the error variance sigma squared, and our estimate is going to be sigma squared hat. All right. And we're going to estimate sigma squared hat by looking at the residuals from the regression. So the residual from the regression is each individual y, or each individual observed dependent variable minus the fitted value for y, the fitted dependent variable. All right, and this is how we calculate it. So we estimate the error variance this way, where we have sigma squared hat, we the estimated sigma squared, all right, the estimated variance of the error term, all right, equals the sum of the squared residuals. So the residuals squared, so the sum of the squared residuals divided by n minus k minus 1. This is our estimate. This is our estimate of the variance of the error term. If the OLS assumptions hold, then our estimate of the error term will be unbiased. That means our the expected value of our estimated error variance will equal the true error variance. So that would be, if all the OLS assumptions hold, then sigma squared is an unbiased estimate of the population error variance. All right. So now that we have an estimate of the error variance, we can now estimate the variance of beta 1 hat. The estimated variance of beta 1 hat is this. All right. So we have the estimated variance of beta 1 hat. So we've got variance of beta 1 hat. There's a hat over that variance of beta 1 hat. So that's what we're saying, the variance of beta 1 hat. All right. And it equals our estimated error variance divided by the total amount of variation in the independent variable times 1 minus the r squared. All right. So from here, again, this is our estimated variance of beta 1. Our estimated variance of beta 1 hat. From here, we utilize the standard error of beta 1. we utilize the standard error of the beta 1 hat distribution in our hypothesis testing. Okay, you can remember this from our first lecture on hypothesis testing. This is very similar to the sample distribution of the sample mean, right? Our t-statistic was the sample mean divided by the standard error of the sampling distribution of the sample mean. You might remember this as well from our introduction to regression analysis and hypothesis testing. What we want to do with our regression is we want to do a hypothesis test on whether or not beta 1 hat is equal to 0. Right? That's our null hypothesis. To test that, we need to create a test statistic. All right? In the test statistic, we use the standard error of the beta 1 hat, or the beta j hat in this example. Well, the standard error is the square root of the estimated variance of beta 1 or beta j hat. All right, so this is where our standard error comes from. So as we have seen before, we test the null hypothesis that beta 1 equals 0 by using a t-test. And we use the t-statistic, so the t-statistic is going to be t equals beta 1 hat divided by the standard error of beta 1 hat. All right, I'm just going to correct that. Let's make this beta 1 hat. All right, so our t-statistic is going to be beta 1 hat divided by the standard error of beta 1 hat. All right, now this is where it all comes together. This is why the variance is so important. We can see it right here. You can remember that when our t-statistic is large enough, we reject the null hypothesis. So we are more likely to reject the null hypothesis if our t-statistic is larger. All right? So the larger the t-statistic, the more likely we are to reject the null hypothesis. So let's play this out. Let's play through the logic. When the variance is large, then the standard error will be large. Let's play this out. When the variance is large, the standard error will be large, because the standard error is just the square root of the variance, all right? So when the variance is larger, the standard error will be larger. When the standard error is larger, what happens to the t-statistic? As the standard error gets bigger, the t-statistic gets smaller. That means when we have a large variation in beta hat, our t-statistic will be smaller and it will be harder to reject the null hypothesis. All right, that's going to be a big problem. And that's what we're going to talk about when we talk about multicollinearity. All right, that's why we want small variances of our coefficient estimates. Is because if our variances are smaller, our standard errors will be smaller, and if our standard errors are smaller, then t's will be bigger, and it's easier for us to reject the null hypothesis. It's easier for us to reject the null hypothesis if there is actually a true effect. It reduces the probability of us committing a type 2 error. Type 2 error is when there really is an effect, but we fail to reject the null. There really is effect, and we say that there isn't. That's a type 2 error. We're likely to commit a type 2 error if our variance of beta 1 hat is large. If the distribution of beta 1 hat is really big, then it's much more likely to commit a type 2 error. All right. With that said, we've laid the foundation. Now we're going to go in and we're going to talk about multicollinearity. To prime that, we're going to review again our assumptions of the OLS, of the ordinary least squares model. All right, so the assumptions of the OLS, ordinary least squares model. So here are the assumptions. I had them in the last lecture. Conditional mean independence, constant variance, which we're going to talk about next lecture. We talked about this one last lecture. The next one, this is the one we're going to focus on today. There's no independent variable is a perfect linear function of another variable. No perfect multicollinearity. All right, this was what we're going to talk about today. Is this notion of multicollinearity. All right, and again, if all the OLS assumptions are true, if all of them hold, then beta 1 hat is blue, the best linear unbiased estimator. All right, all right, and then here we go. I can even explain what this means better. When I said best, all right, best linear unbiased estimator. What do we mean by best? What we mean by best is that it's the most precise. It's the most precise. It's the most efficient possible estimator. It's the most precise estimate that we can get of the true population beta 1. It's the best. It's the most precise. That's what we mean when we say best. It's the most precise. It's linear. Again, that just means that it's a parameter from a linear model. And unbiased. That means that there is no bias in the estimate of beta 1, right? So that's what we talked about last time. If there's no omitted variable bias, then the estimate will be unbiased, all right? And again, it's an estimator because it means it's an estimate of the true beta 1. All right. So we want this. We want beta 1 hat to be blue. We want it to be the best linear unbiased estimator. So it means that we're very concerned with whether or not these assumptions hold. Last time we talked about the conditional mean independence assumption, and we were very concerned about omitted variable bias. Next time we're going to talk about this constant variance assumption, and today we're going to talk about assumption number 3. All right, we're going to talk about assumption number 3. Multicollinearity. So let's do it. Let's talk about multicollinearity. Let's talk about assumption number 3. What is multicollinearity? All right. So assumption number 3 says that there is no perfect multicollinearity in the model. Perfect multicollinearity is when two independent variables are some perfect linear relationship of each other. So 2 or more. Could be more than 2. We'll see example of more than 2 later. Here's an example. Let's look at some data where this would be the case. We have 3 individuals, all right, so indexed by I, and we have variable x1 and x2. So for all 3 of our individuals, we have variable x1 and variable x2. x1 equals 1 for each individual, and x2 equals 2 for each individual. These variables are a perfect linear relationship of each other. What do I mean by that? Well, let's look at it. In this case, x2 equals 2 times x1. It's a perfect linear relationship. There's no error. There's no variation in it. You can produce x2 just by multiplying x1 by the number 2. It's a perfect linear relationship. There is no error. There's no differences. It's just a perfect linear relationship. So in this case, the model wouldn't work. This is perfect multicollinearity. It violates the assumptions of the model. And in fact, the regression will not even work if you have perfect multicollinearity. You can't even calculate the coefficient if you have perfect multicollinearity. All right. But now, we also will have a problem even if we don't have perfect multicollinearity. We could have imperfect multicollinearity, which we'll just call multicollinearity, just generically, is when 2 independent variables, 2 or more, are some imperfect linear relationship of each other. We might say that they're highly correlated. All right. So here is the example again. x1 equals 1 for all 3. x2 is 2, 2, and then 1. So in this case, x2 equals 2 times x1 plus some error term. There's some differences between them. So you don't get x2 just by multiplying x1 by 2. Because, in this case, the error term would be 0. In this case, the error term would be 0. But in this case, the error term would be negative 1. All right, so they're not a perfect linear relationship, but they're close. They're very, very close to a perfect linear relationship. All right, so we would say that x1 and x2 are highly correlated. This would be an example of multicollinearity. They're collinear. They're closely related to each other. They're close to a linear relationship with one another, but it's not perfect. All right, now assumption number 3 says that there's no perfect multicollinearity. If we have perfect multicollinearity, then we have a huge problem. We've got a big problem. All right. In fact, the regression won't even run as stated. But even if we don't have perfect multicollinearity, we just have some amount of multicollinearity, we will still have a problem. All right, so let's break this down. Multicollinearity. Multi means more than one variable. Collinear, one variable is a linear function of the other. Practically, there's usually some degree of multicollinearity between variables. This is equivalent to saying that there is some amount of correlation between variables. All right. Multicollinearity becomes a problem when there is high correlation between two or more independent variables, or when there is perfect multicollinearity. All right. And I'm actually going to make this even more clear. It's even more specific. Multicollinearity becomes a problem when it interferes with our ability to conduct hypothesis testing. I'll make that more clear. All right, now let's drive this point home. Let's try to understand why this is an issue by looking back at our estimated variance of beta 1, or beta j. Okay, now if you remember from the discussion that I just had about variance, we want our variances to be small because that will reduce our chances of committing a type 2 error. All right, it affects our hypothesis testing. All right, so so now let's direct our attention to this term here. Before I downplayed it. I didn't talk about it as much. Let's talk about it more now. 1 minus rj squared. All right, so rj is the r squared value taken from a regression of the independent variable xj on all the other independent variables. So if we were looking at the case of x1, it would be the r squared taken from the regression of x1 on x2 and x3. All right, we want smaller variation in this beta j hat. Therefore, we want to reduce sigma squared and increase SST. This will give us more precise estimates. All right, that's what we talked about before. But now let's tie this in. But as rj squared will be larger as, but rj squared will be larger as x1 is more closely related to or explained by x2 and x3. Therefore, if your independent variables are highly correlated, this will increase your variance. This will increase the variance of the coefficient on the variable that you're looking at. So if we're thinking, let's think about this as beta 1. So beta j, this is kind of the generic case for any variable xj. Let's think about it as x1. The variance, the estimated variance of beta 1 hat, will be larger as the relationship between x1 and the other independent variables is larger. So let's look at the math and we can see it. As the relationship between x1 and the other independent variables is larger, as the relationship between x1 and then x2 and x3, as that relationship is larger, then the r squared will be larger. As the r squared is larger, 1 minus the r squared gets smaller. That means the denominator is smaller. That means the fraction is bigger. So that means the more closely related x1 is to x2 and x3, the higher the estimated variance of beta 1 hat will be. And then that becomes a problem if it makes it difficult for us to do hypothesis testing with beta 1 hat. All right. So as r squared goes up, then 1 minus r squared goes down, it gets smaller, which makes the variance of beta 1 hat get bigger. Therefore, the correlation between x1, x2, and x3 can make your beta estimate, your beta 1 hat estimate, imprecise. And this is the multicollinearity problem. Is it makes your beta 1 hat estimate imprecise. If x1 is a perfect linear function, all right, so now let's do perfect multicollinearity. If x1 is a perfect linear function of x2 and x3, then R1 squared will be 1. The R squared value from this regression, if it's a perfect linear relationship, then the R squared will be 1. So in that case, 1 minus R squared equals 0, which makes the denominator 0, which makes the variance infinite, and the regression breaks down. In fact, you can't even run it as specified if you have perfect multicollinearity. This is the perfect multicollinearity problem. This is the perfect multicollinearity problem. All right, so let's summarize the problem. So multicollinearity, when it's not perfect, is when two or more independent variables are highly correlated. They are closely related. They are so closely related that they are almost a linear function of each other. This makes your variance. This makes the variance of your coefficients higher. This makes your coefficient estimates imprecise, which will cause a problem in your ability to perform hypothesis tests. Now, and I want to be clear on this, this problem only affects the variables that are involved. That means it only affects the variables that are multicollinear. If a variable x1 is multicollinear with variable x2, then you will have artificially high standard errors for the coefficient on x1 and x2. That means it'll be difficult to do your hypothesis testing on the coefficients from the variables x1 and x2. All right. Perfect multicollinearity is when two or more independent variables are perfect linear combination of each other. In this case, the regression will not run as you've specified it. In practice, one of the collinear variables will be dropped from the regression. I'll give you an example of this in the demo and later in the lecture. Okay, so that is the multicollinearity problem. If you have multicollinearity, it will increase the standard errors on your estimates, the coefficient estimates for those variables. That will make your estimates imprecise. That will make your t-values smaller, make your standard errors bigger, make your t-values or your t-statistics smaller, make it less likely to find a significant result, makes it more likely to commit a type 2 error. If you have perfect multicollinearity, then the regression won't even run as stated. One of the collinear variables needs to be dropped from the model. All right, so how do we test for multicollinearity? How do we know that we have it? How do we know that we have a problem with multicollinearity? We're going to talk about that next. Then we're going to talk about solving it. Then we'll go into the demo. All right, so testing for multicollinearity. How do we test for it? How do we know that we have the problem? How do we know that we have a multicollinearity problem? Actually, even before I go into this, the very first thing that you should do when you're thinking about multicollinearity is that you should think about it intuitively. You should look at your variables, try to understand your variables from an intuitive standpoint. Think about them. Do you think that any of them are going to be really highly correlated? Use your intuition. Use economic theory. Are any of them going to be highly correlated? If so, you might want to keep your eye on them to see whether or not you have multicollinearity between those variables. All right, that's your first test, is your intuition. Think about the model. Think about what variables make sense. Think about what variables might be highly related to each other. Okay, but then now, kind of a more structured test is what we do is we check the variance inflation factors. The variance inflation factor, or VIF, for some variable j, the VIF for some independent variable j is equal to 1 divided by 1 minus r squared j. All right, so this r squared j, again, this is the r squared value taken from the regression of xj on all the other independent variables. The variance inflation factor comes directly from the variance of beta 1 hat. You can see that the variance of beta 1 hat is sigma squared divided by SST times this term, by 1 minus r squared j. we can just pull that out. We can say this is equal to sigma squared divided by SST times the variance inflation factor. So the variance inflation factor, basically, it's just a measure of how much the correlation between the independent variables increases the variance for the corresponding coefficient. And the rule of thumb, just kind of the standard in the field, is that if the variance inflation factor is greater than 10, then we have a multicollinearity problem. So if the VIF is greater than 10, then we have a multicollinearity problem. All right. And when I mean problem, what I mean is that there is multicollinearity. All right. Now, as I go on, I'm going to make it even more clear. Sometimes we have a multicollinearity problem. That means there's multicollinearity, but it's not really a problem for us. All right. And I'm going to make that clear in this lecture. Be sure to keep your ears peeled for that. Peeled? Does that make sense? People say that? Your ears peeled? No, I don't think so. Your ears open. Your eyes peeled, ears open. That's it. All right, so keep your ears open for explaining when multicollinearity really becomes a problem. All right. All right, so that's how we test for it. Step number 1 is use our intuition. Step number 2, check for the variance inflation factors. All right. Now, the last step is we're going to look into how do we solve the multicollinearity problem. How do we solve it? So if we have it, how do we solve it? All right. Solutions for multicollinearity. Perfect multicollinearity requires that you must drop one of the collinear variables. Typically, we know when two variables are perfectly collinear, and we simply do not include both variables. An example of this is called the dummy variable trap. I'm going to talk about that now. I talked about it briefly in the last lecture. I'm going to demo it in Stata later. So let's take kind of a standard example here of a dummy variable trap. So let's go back to our model from the past. At some point, we've run this model, last lecture perhaps. And so this is our model of wages. All right, we've got wage as a function. We've got wage as a function of education, experience, non-white, female. And then in this case, I'm adding a dummy variable for male. All right, I'm adding a dummy variable for male. So female equals 1 if the person is female. It equals 0 if the person is male. Male equals 1 if the person is male, and equals 0 if the person is female. So here I've included a dummy variable for female and for male. So if we think about this, from last time, why didn't we include a dummy variable for male? What if we wanted to know what the impact of being male is on wages? That we might be interested in that. Might we want to know that? I think we might want to know what the impact is of being male on wages. So why not include both? Why not include a dummy variable for female and a dummy variable for male? Because that way we can know what's the effect of being female, beta 4, what's the effect of being male, beta 5. Why can't we do that? Why didn't we do that? The problem is that female and male are perfectly collinear with each other. Female just equal 1 minus male. So the regression will fail as specified. This regression will not run. This regression won't work. You won't be able to do it. You won't be able to calculate it because you cannot run a regression that has perfect multicollinearity. That's why we don't include both. We don't include a dummy variable for both possible values or both possible characteristics of the dummy variable. We don't include a dummy variable for female and a dummy variable for male. We only include one of them because the regression will not work. It won't run because there will be perfect multicollinearity. You'll have to drop one of them. You'll have to drop either male or female, or else the regression won't run. And when you run it in Stata, it'll drop it for you. We'll see it a little bit later. So we either have to drop female or male because it will not run if you have perfect multicollinearity. Well, what if we want to know what the impact of being male is on wages? Well, we interpret beta 4 hat as the relationship between being female and wages relative to being male. So we interpret this coefficient as something relative to being male. So we could say let's say it's the effect of being female relative to being male. So let's use an example. So if beta 4 hat is equal to negative 0.5, then we would say that women make 50 cents fewer dollars per hour than men. All right, so this is a measurement. This is a value that is relative to men. So beta 4 hat is interpreted relative to men. So we capture the effect of being male by interpreting the coefficient on female. But we also could just switch it around. We could get rid of female and include male. In this case, we could include male instead. In this case, we interpret beta 5 hat as the relationship between men and wages relative to women. And in this case, beta 5 hat would be equal to 0.5 because it's just the reverse of the female variable. Here we would say that men make 50 cents more dollars per hour than women. It's the exact same thing as we said before. Women make 50 cents less versus men make 50 cents more. All right, so they're just the reverse of each other. So we only need to include one. Now this will also come up if we're breaking out a categorical variable. Now, if you remember, 2 lectures ago, I believe we talked about the kitchen sink model. We talked about specifying a regression model, and I gave an example of a model that has. A bunch of different dummy variables for all the different kinds of jobs, right? And I said that you can't include a dummy variable for each of the possible jobs. So in this example, we had 4 jobs, and we include only 3 dummy variables. So a dummy variable for each of 3 jobs. We exclude one of the 4. Well, that's because if we included all 4, we would have perfect multicollinearity, and we wouldn't be able to run the model. It also means that every time we interpret one of these coefficients on these 3 job variables, we interpret it relative to the job that is excluded from the model. I'll make that more clear when we get to the demo. All right, so this is the dummy variable trap. This is a long explanation of an illustration of perfect multicollinearity in the most common situation you'll run into. All right, and you solve it just by dropping one of the collinear variables. And in fact, Stata will do it for you. All right. But now, how do we solve just multicollinearity when it's not perfect? So when you have multicollinearity, there are a few solutions. The first is get more data. So we increase our sample size. By increasing our sample size, we make our estimates more precise. We talked about this earlier. You increase the sample size, and that will decrease the variance of your coefficient estimate. And so if we increase our sample size, we might be able to compensate for the effect of multicollinearity. The next possible solution is to drop one of the variables. So if we have variables that are highly multicollinear, then you can drop one of those variables from the model. We just drop one of them, and then we get rid of the multicollinearity problem. However, we have to be very careful before we drop variables, because I said in the last lecture, we really do not want to exclude important variables because we do not want to have omitted variable bias. So when choosing what to do, you have to decide what's worse, the omitted variable bias or the increased variance. Typically, we will only drop a collinear variable if we think that it is irrelevant to the model. That means how do we put it? That means the omitted variable bias problem is a much bigger problem than multicollinearity. We're much more concerned about biasness than we are about, or I should say we're more concerned about bias than we are about efficiency. They're both important, but we will typically not exclude a relevant variable. It will be a rare case for us to exclude a relevant variable in order to solve the multicollinearity problem. Okay, so typically we will only drop a collinear variable if it is irrelevant to the model. All right, the next one, combine multicollinear variables. Sometimes multicollinear variables share a common theme, and you can combine them into one coherently defined variable. So sometimes multicollinear variables share a common theme, and you can combine them. This isn't necessarily an interaction term. This is combining them in some meaningful way. That could be an interaction term, but oftentimes it's something different. Let me give you an example. So imagine that you're studying factors that determine whether or not a child is born prematurely. All right. So we specify the following model. So here is whether or not a child is born premature. And we think it's a function of the education level of the household head, of the household. And we think that it's a function of whether or not the mother has access to a doctor. And it's a function of whether or not the mother has access to a hospital. And it's a function of whether or not the mother has access to neonatal medicine. All right, so here's our model. Our model of whether or not a baby is born prematurely. A function of the education of the household head, a function of access to a doctor, access to a hospital, access to medicine. Well, we can look at these three variables and say, actually, these are probably going to be very closely related. There'll probably be a high level of multicollinearity between these variables. Because if you have access to a doctor, then you probably have access to a hospital, which means you probably have access to medicine. If you have access to a hospital, you almost certainly have access to a doctor and to medicine. So these are going to be highly multicollinear. Well, then we could solve this multicollinearity problem by combining them into one variable. Why don't we create a variable and we call it healthcare? And we say healthcare is a dummy variable that indicates whether or not you have access to some form of healthcare. And it equals the doctor variable plus the hospital variable plus the medicine variable. And so now we change the model. So now it's education plus the healthcare variable. We've combined them. So now we've replaced it. This variable captures all three variables, so we don't have an omitted variable problem because the healthcare variable captures all the effect of the other three variables, but there aren't several variables that are multicollinear. And so now this is solve the multicollinearity problem by combining variables into one coherent, meaningful combined variable for healthcare. All right, and then lastly, the last solution is do nothing. All right, so we try our best to solve the problem using solutions 1, 2, and 3. And after that, we admit that we have a problem, we talk about how it affects the results, but we do nothing. And oftentimes this is what happens. As we go through the demo, I will show you an example. We'll kind of get to that point. We'll kind of say, okay, well, when do we call it quits? When do we say, all right, we've done everything we can, and we're just going to have to live with the amount of multicollinearity that we have? All right, so we'll show that. All right, and with that, let's switch over to Stata and do our demo. All right, pull this over to the right. Pull this over to one side. Excellent. And let's open up our data set. All right, I'll post that online so you can have access to it. Wages 3. All right, so let's get started. Lecture 6, multicollinearity and goodness of fit. All right, boom. So let's do it. Let's start. First, let's talk about goodness of fit. We're just going to kind of polish up that conversation. Fit. All right. Let's run a model so that I can just kind of show you how to calculate those goodness of fit variables from the Stata regression output. The Stata regression output is kind of neat in terms of what it presents to you. So let's run kind of a basic model. Wage regressed on education. experience. Now you'll notice in wages 3, there's some different variables in here. I have a different variable for education. It's just edu instead of educ. I also have a variable called children. I've also included the dummy variables for all the different job types. All right, so there's a couple differences in this data set. All right, so we're going to regress wage on education, experience, and female. This was a good model that we had from last class. So let's run that. All right, so here's our results. Now this is what I want to point you to this time. Now we know before that we had r squared here, and we had adjusted r squared here, right? But now I haven't ever talked to you about what this is. I've never talked to you about what this information is here. Well, let me show you what it is here today. SS, sum of squares. All right? This SS is this, okay, I'm going to show you what this is. All right, let's go back to our goodness of fit. All right. Sum of squares. So remember, we have the sum of squared explained. That means how much is explained by the model. We have sum of squared residuals. That means how much variation is explained by the residuals. And then we have the total sum of squares. That means how much variation there is total. Well, look at what we have here. Model. That means the sum of squares explained. So this is the total amount of variation in the dependent variable that is explained by the model. And what do we have here? Residual. This is the sum of squared residuals, the total amount of variation in the dependent variable that is explained by the residual, or that is not explained by the model. And then total. So this is the total amount of variation in the dependent variable. Now remember, how do we calculate our r squared? It's the sum of squared explained divided by the sum of squared total. Let's calculate it. All right, so the sum of squared explained, that's how much is explained by the model, so that's here, 2236, all right, I'm just going to round it off, divided by the total, divided by 7222. And what do we get? 0.3096, what do we have here? 0.3096. Ha, there we go. We have it. That's the r squared. We've calculated it here. Now, we could also do the same procedure. We could also use this information to calculate our adjusted r squared, but I won't do that here in the lecture. But you might have to do it in an assignment. All right, so just be ready. All right, so there we go. That is the calculation of r squared and adjusted r squared using our Stata output. All right, so that's all I wanted to show you there. Just kind of put some meat on the bones there. So let's move on from there. Let us talk about multicollinearity. Let's talk about multicollinearity. Okay, where should we begin? All right. First, let's run a model in which there might be multicollinearity. Multicollinearity. All right, that's what we're going to do now. And we're going to do a couple different examples here. All right. Now, first, what did I say first? First is we think, what variables might we have a multicollinearity problem? First, what variables might be collinear? All right, so that's where we start. What variables might be collinear? So let's think about it. Let's look through our variables. Let's look through our variables. Do we think education and experience might be collinear? They could be. If we think about it, the more years of experience you have, or let's put it the opposite way. The more years of education you have, probably the less years of experience you have. Because if you spent a lot of years in school, those were years that you didn't spend gaining experience. So these might be collinear. What about ethnicity? Probably not a high level of correlation. Gender, it's not obvious. What about married? Again, it's not obvious. Okay, I've added here a variable called children, the number of children. Okay, well, let's think about that. The number of children that a family has, that an individual has, might be correlated with whether or not they're married. Married people are probably more likely to have more children. So, actually, that's probably a big one. I bet that there's a ton of multicollinearity between married and children. Okay, so let's think. There might be some multicollinearity between some of these different job sectors. But okay, let's start with just our first two. The first intuition we have is that education and experience might be collinear, and then married and children might be collinear. So let's think about those two examples. All right, so education and experience, those might be multicollinear, and married and children might be multicollinear. So let's do this first. Which one should we do first? What do you think? Let's do married and children first. Let's take a look at that. All right, so let's exploring multicollinearity between married and children. All right, now we can do this a number of different ways. If you remember from the lecture, what we're concerned about is this 1 minus r squared term, right? We're concerned about this 1 minus r squared term. And the 1 minus r squared term is the r squared that's taken from the regression of the independent variables on each other. So we can get an idea of whether or not we think we're going to have multicollinearity by running a regression of the variables that we think might be collinear. So let's regress married on to children. All right, so now married is going to be our independent variable, and children is going to be, married is going to be our dependent variable, and children will be our independent variable. So let's run it. All right, what's r squared? Wow, okay, r squared is very high. All right, r squared is very high. That means 1 minus r squared is going to be very low. That means that the variation on the coefficient of married and the coefficient of on children in a regression of wage on those will be very high. There'll be a large variation. All right, so that would make us think that we're going to have a large variance. We're going to have a large amount of variance if we were to add these to our model. So let's do it. Let's add married and children to our model, and let's run it. All right, because we've done this regression, we found this large r squared. We think that the coefficients on married and the coefficient on married and the coefficient on children is going to have a very large variance, which means it'll have a very large standard error. Well, let's check that. Let's confirm that. Let's look. All right, so we've got the married variable and the children variable. Well, what do we have? Here is a very large standard error. It's a very large standard error, very small t-statistic, and therefore it's not significant. Same thing with children. Children has a large standard error. It's not too large. The coefficient's very small. Very small t-statistic, highly insignificant. Highly, highly insignificant. Okay, so now we look at this and we think, we've run this regression. We think, all right, wage is a function of education, experience, female, whether or not the person is married, and how many children they have. But we look at this regression, we find that these two variables are insignificant, and we think about that, and we think, okay, they're insignificant. Am I committing a type 2 error here? I know that these two variables are highly multicollinear. At least I think that they are. Based on my intuition, based on my regression, I think that they're multicollinear, which means the variance of these coefficients are large, the standard errors are large, the t-values are small, and therefore we reject the null hypothesis. All right, so I think I have a problem here. I think I have a multicollinearity problem that is going to make it hard for me to reject the null hypothesis. The null hypothesis that this coefficient equals 0 or this one equals 0. All right, so let's test for it. Let's do our formal test. Not a formal test, but Let's calculate the VIFs. So all we do is we type VIF after the regression, and we'll run it again. Okay, let's look. Wow. All right. Here's our variance inflation factors. There are very high variance inflation factors. Now remember that if the variance inflation factor, let's see, where is this? If the variance inflation factor, or in the solving part, there it is. If the variance inflation factor is greater than 10, then we would typically say that we've got a multicollinearity problem. That means those variables are multicollinear. If we look here, experience and education, we were right. There is multicollinearity. There's big time. And married and children are multicollinear. Very large VIS, very large variance inflation factors. All right, so we have multicollinearity in all 4 of these variables. All right, now let's focus on married and children for now. We're going to come back to education and experience in just a minute. So if we look at married and children, these two are definitely multicollinear. That means that those standard errors are going to be larger than they should be. All right, so let's write this down. Definite multicollinearity between married and children. All right. So there's definitely multicollinearity there. Now, what problem does that cause? It increases the standard errors and it makes it hard to reject the null. All right. It increases the standard errors and makes it hard to reject the null hypothesis. All right, so now let's look here. Both of these variables are insignificant. That means that this multicollinearity issue, there's definitely multicollinearity. That means that the multicollinearity issue is actually a big problem for us, or it could be a problem for us. The multicollinearity is making these standard errors large. That means even if being married or having children actually has an effect, it's going to be very hard for us to see it because the standard errors are so large. And so we potentially have a problem here, and we need to try to fix it. So how can we fix it? How do we fix the problem? All right, what are our options? Option 1 is more data. All right, well, we don't have that option. All right, option 2, drop a variable. All right, we'll talk about that in a second. And let's separate these. More data. We don't have more data. Okay, so that's not a solution. So the next option is drop a variable. Let's talk about that. All right, we drop a variable. Now, what did I say? What did I say about dropping variables? We only drop a variable if we think that it is not relevant. Otherwise, we would have omitted variable bias. All right, we don't want omitted variable bias. So the question is, do we think that married or children is an important, relevant variable? Well, let's say for the moment, let's say that no. Let's say that we don't think that children matters. Really, it's marriage. So let's rerun the regression where we've dropped children from the model. So we're regressing wage on education, experience, female, and married. All right, we've dropped children from the model. Oh, whoops. Using the old name. All right. All right, now let's look at this. We've dropped we dropped children from the model. Actually, I'm going to run the other one right after it so we can compare it easily. All right. So here we go. Here's our model where we've dropped children. So now we have education, experience, female, and married. Now, once we've dropped children, we find the standard errors are much lower. Look, that standard error is 0.29. Before, the the standard error on married was 1.39. It's much, much smaller. All right, so there was a huge multicollinearity issue there. So once we drop children, then married, the standard error is much smaller, which implies that the t-statistic is much bigger, which implies that, okay, actually now we've rejected the null hypothesis. So the null hypothesis for each of our coefficients is that the coefficient is equal to 0. We're rejecting the null hypothesis, which means that we have evidence to suggest that married, that there is a significant relationship between wages and being married. All right. Well, that's great. There was a multicollinearity issue here. There was a big problem. That means married was actually statistically significant, but we couldn't see it. We couldn't see that it was significant. We couldn't see that there was a relationship between wage and married because we included this other variable that it was multicollinear with. And so once we dropped the children variable from the model, now we're able to see the effect of marriage on wages. Okay, so this is kind of a success. But now, again, we have to be careful. We don't want to create. We do not want to commit omitted variable bias. That means we don't want to drop children if we think that children is relevant. Now, is there any way that we can get an idea of whether or not the children variable was relevant to the model? Is there any way that we can get an idea on that? If we look at this regression and we look at children, it's highly insignificant. Okay, sure, but that might be because of the multicollinearity problem. I can't conclude from this that it's not relevant because I know that it's multicollinear. So I know that this p-value is going to be much larger than it should be. So is there any other information that I can use? Is there any way that I can compare these two regressions and get an idea of whether or not children is relevant or not? Is there any way that I can get an idea of whether or not I'm committing omitted variable bias, if I'm creating omitted variable bias by dropping the children variable? Well, actually, I think we can. I think that there is evidence by comparing these two. What's the evidence? If you look at the coefficients on all the other variables and you compare them between the models, you can get an idea of whether or not you've created omitted variable bias by excluding children. If you remember from the last lecture, when you have omitted variable bias, that changes the coefficients. That changes the coefficients on the other variables in the model. So if you have omitted variable bias, you're creating, you're causing bias, you're causing changes in the other coefficients in the model. And so, if you drop a variable from the model, you can get an idea of whether or not you're creating omitted variable bias by looking at how dropping that variable affects the other variables in the model. So let's take a look. So here are all of our coefficient values for the other four variables with children in the model. Now, we drop children from the model. What happens? Well, with children, we have education is 0.65. Without children, education is 0.65. With children, experience is 0.93. Without children, experience is 0.93. With children, female is negative 2.07. Without children, female is negative 2.07. With children, married is 0.65. Without children, married is 0.65. They don't change. They hardly change at all. That is really good evidence that children is not relevant and that you're not creating an omitted variable bias by excluding it from the model. So in this particular example, just dropping the children variable would be the best way to solve it. Just dropping the children variable would be the best way to solve the multicollinearity problem. All right, but let's explore one other option. Let's say you still think that children is going to be relevant. All right, so let's come up with another one. Combine variables into some coherently defined new variable. All right, that's our third solution. What would that be like? So we know that married and children are multicollinear. They're highly related to each other. So what we could do to solve that, another way of solving it would be to combine them in some way. You could multiply them together, create the interaction term, but I'm thinking something a little bit different. Why don't we create a new variable? We're going to do gen marchild. All right, this is going to be a variable. This is going to be a variable. It's going to be a dummy variable for if the person is married with children. Or actually, no, scratch that. This is going to be a variable. This is going to be a dummy variable that will be 1 if the person is married or has a child, or both. It'll be 0 if they're neither married nor have a child. All right, so I'm going to do gen marchild equals 0. Replace marchild equals 1 if, how does this work? If married equals 1, or this vertical bar is or in Stata, or if children is greater than 0. So now this marchild variable is going to be a dummy variable. It will be 0 if the person is not married and has no children, and it will be 1 if the person is married and has children, at least one child. So I'm going to create that variable. Now I'm going to rerun the regression. Experience, female. I'm going to replace both married and children with the new variable, marchild. And run it. Okay, and then here we go. Again, these coefficients, the coefficients in the other variables are all very similar. The coefficient on marchild is very similar to the one on married, and it's also significant. Okay, so this solves the problem too. So if we're still worried about variable bias, we combine them into one coherently defined variable. Now, before you combine variables, you have to be very clear that it actually does make sense, that the combined variable makes sense. You can't just combine any two variables. The variable, you have to think creatively to think of a variable that makes sense. All right, I'll give an example of one that wouldn't quite make sense in just a minute. All right, and then what's the last solution is do nothing. Well, in this case, we can do either solution 2 or 3. We can do either solution 2 or 3. And both are good. Both work. So we're not going to do nothing. We can solve it. So we just solve it. We just solve it using solutions 2 or 3. So we can say we don't do nothing. All right, there we go. Now, let's explore the multicollinearity. Let's explore the multicollinearity between education and experience. All right, and experience. All right, let's do that now. All right, so let's set ourselves up with a model here, and we're just going to do wage on education, experience, female, and then married. All right, we're going to exclude children. We don't need it. We already showed that we can do it without children. All right, and then let's calculate our variance inflation factor, and let's calculate it. All right, so now here we go. Again, education and experience are highly correlated with each other. We can tell. There's a lot of multicollinearity there. And that makes sense intuitively. It makes sense intuitively. We can even confirm that for ourselves. Let's regress education on experience, and we'll show ourselves the same issue. All right, so as you have more experience, you have less education. That makes sense, because if you spend a lot of years in school, you probably have less experience in the workforce. And the R-squared is very high. All right, these are very closely related to each other. All right, so now we have a we have a multicollinearity issue here. Experience and education are highly multicollinear. So let's think. How do we solve the problem? One is more data, but again, we don't have more data. All right. 2 is drop a variable. So let's talk about that. Now, we only want to drop a variable if we think that one of the variables is not relevant. Do we have any reason, based on intuition, based on theory, based on the models, do we have any reason to think that either education or experience is not relevant? I think that they're probably the 2 most relevant variables based on intuition. And so I'm very hesitant to drop one of them. I think if we dropped one of them, we would find that we have quite a bit of omitted variable bias. Well, let's just drop one to see. Let's use the same technique we did before. Let's drop one of them, and let's see what it looks like. All right. So actually, let's think about this first. Let's think about, actually, I want to write this in. Let's drop experience. All right, we're going to drop experience. We think this is going to probably create omitted variable bias. All right, what's the sign of that bias? Let's review from last lecture. What's the sign of it? What is the sign of that bias? Well, we figure out the sign of the bias by first considering the correlation between education and experience. Is the correlation going to be positive or negative? I think it's going to be negative. We can even see that in the regression we ran. It's negative. All right. That is more experience, less education. More education, less experience. All right. And then now the correlation between experience and wage. I think that will be a positive correlation. All right. So based on those 2 things, we'll probably have a downward omitted variable bias. Let's check it out. We've dropped experience. Let's see what happens. So if we have a downward omitted variable bias, that means that the coefficient on education should decrease. Okay, wow, big time. The coefficient on education shrank tremendously. There is a huge amount of omitted variable bias on the education coefficient. You can see the other ones changed too. So the coefficient on female went down. The coefficient on married went up. We have a ton of omitted variable bias by dropping experience from the model. Okay, so solution 2 does not work. We would have omitted variable bias. All right, so we definitely can't do 2. What about 3? Coherent combined variable. All right, so now what kind of combination variable can we come up with? So now here's the thing. We have to come up with a variable that makes sense. We have to come up with a variable that's coherent. It meaningfully combines the 2 variables. We can add them together, but what would that mean? What would it mean if you added it together? Maybe we could add it together. What would that look like? That's the number of years of education plus the number of years of experience. You know, I guess if you think that that years of experience and years of education can kind of be treated the same, then you can combine them. I don't know. That doesn't make quite as much sense to me as the married with children variable. As we think about it, it's not obvious how you can compare education and experience. I think they're 2 very different things. And so it might be hard to do this. It's hard to create a coherent combined variable, some variable that makes sense. All right, so then what's solution 4? Solution 4 is do nothing. Well, let's think about doing nothing here. Let's rerun the original one. Take a look at this. What's the problem that's caused by multicollinearity? What's the problem? Remember when we did our marriage example? Let's go back up. Let's find our marriage. Where's marriage with children? It's quite a few regressions ago. Here it is. Remember our problem. What's the multicollinearity problem? It increases the standard errors. That's the problem. That's what we don't like. We don't want our standard errors to go up, right? That's what we're trying to avoid, is an increase in the standard errors. Well, why is that bad? Why is that a problem for us? Well, it's a problem because larger standard errors give smaller t-values. Okay, why is that a problem? That's a problem because it increases the chance of committing a type 2 error. It makes it difficult to detect a significant effect. Okay, now that was an issue for the married variable because we found the married variable was insignificant. And we thought, okay, well, but there's a lot of multicollinearity. Maybe married is significant, but I can't see it because of the multicollinearity problem. But what's happening here? Look, even though education and experience are highly multicollinear, both of them are still significant. Both of them are still significant. So that means we have to ask ourselves, all right, yeah, we've got multicollinearity for sure, but is it actually a problem? Like, is it a problem? We have multicollinearity, yes. But is it actually a problem? Because what does multicollinearity do? It increases your standard errors. It makes it harder to detect a statistically significant effect. But we find that they're significant. That means in this case, there really isn't a problem. All right? So I want you to remember this. This is important. If you have multicollinearity between variables, but those variables are still significant, then you don't really have a problem. Yes, the multicollinearity is there. Yes, it's increasing your standard errors. Yes, it's decreasing your t-statistics. But it's not causing a problem for you because they're still significant. Multicollinearity is only a problem if it causes a variable that is actually should be significant and makes it insignificant. That's when multicollinearity is really an issue. All right. So in this case, we do nothing. We do nothing because the multicollinearity issue is not really a problem. It's not really a problem because education and experience are both significant. All right. So there we go. 2 examples of multicollinearity identified. So we thought about it conceptually. We explored them rigorously. We solved them constructively. All right. So 2 examples of solving the multicollinearity issue. I'm going to do one last thing. I'm going to illustrate perfect multicollinearity. All right. How am I going to do this? Well, this is going to be straightforward. I'm going to fall into the dummy variable trap and then just show you what happens. All right. So let's do education, experience, female, and then we're going to add the dummy variables for each of the categories of jobs. All right. So you can work in manufacturing, you can work in management, you can work in sales, and you work in the service sector. So I have a dummy variable. So there's 4 different possible jobs. Let me show that to you. Tab, job. There's 4 different job types. I'm going to include a dummy variable for each of those job types. Let's see what happens to the regression. Oh, I forgot to put reg. That's important. All right, let's run this. Like I said, it won't run as specified. It will drop one of the regressors. All right, so it dropped one of the variables. Why did it drop it? Look at this. There's a sale coefficient 0. It says omitted. The regression Stata omitted it automatically, and it omitted it because manu, mana, sale, and serve are perfectly multicollinear. You can't have all of them in the regression. This is the dummy variable trap. You have to drop one of them. Whichever one you drop, see, we have to drop one of the dummy variables. All right. Whichever one we drop, the one we drop is the reference group. So the one that we drop is the reference group. That means we interpret the coefficients relative to the one that we've dropped. So let's drop the service sector. So do wage, education, experience, female, manu, mana, and sale. So now we're going to drop one. Okay, it runs fine. Now we find that all of our dummy variables are statistically insignificant. So that means we would basically treat them like they were 0. But just for the purposes of illustrating how to interpret these, I'm going to think about them as if they were significant for the moment. And the way that we interpret these coefficients is we would say this. If you work in manufacturing, or people that work in manufacturing, on average, make 20 cents per hour more than people that work in the service sector. The service sector is the one that we dropped. The service sector is the one that we dropped from the model. So that's our reference category. So people that work in manufacturing make 20 cents more per hour than people that work in the service sector. People that work in management make 15 cents less per hour than those that work in the service sector. People that work in sales make 23 more cents per hour on average than people that work in the service sector. Okay, but actually, because they're all statistically insignificant, I would interpret them all as 0, and I would say that there's no significant relationship. All right, so there we go. There we have it. That is it for today. Please let me know if you have any questions, and I hope that you have a fantastic day.